this year in our sector, personally I was occupied mainly with book. We, in collaboration with Free Brussels University, namely with Mark Enu, we finished finally the writing book about the cosmological singularity. And this was the main part of time was consumed by this work.
When you are publishing?
In January, we will send this to the Cambridge University Press. This was our main work. Also, the current scientific work was dedicated to the supergravity. The supergravity, which we developed in the past year and this year, is a very technical things. And to show you all these formulas and so on is nonsense, especially in the astrophysical audience. Then I decided to tell you just by words to explain this work, and in the course of history to show you the place of our work in historical development of the so-called integrable models in supergravity. Then the story was, you see, from the Scott Russell, who observed the first solitary wave in the Edinburgh. And you see that the very big, the development was going to have been not very fast, because the first the observation was in this year, but the first solution for solitary waves in the liquid was found by Business. And the fundamental result appeared only in this year when Dr. Beck and de Vries constructed the exact equation, hydrodynamical equation from which we can extract the solitary waves.
Just a moment. I would like to mention that if you like, there are papers written, but you can see these subatomic waves in shallow water in Pescara. If you go to a Montesilvano where you have the sun, and you see definitely the two waves, which are exactly in shallow water, subatomic, crossing each other and keep you going without any so beautiful thing that you can go on the beach where it becomes shallow to a Montesilvano. Spectacular.
At the beach in Francavilla al Mare, you can see extremely clear picture of the solitonic waves.
Of course, in Francavilla it's even better, but if we walk to Pescara, you can see that. And it's fantastic. Simple and clear, that's what you said.
Okay.
Well, but please
Then
do that, go and see.
Then again, a lot of time passed, and in 1940, Fermi, Enrico Fermi, was interested in the behavior of this of the a set of particles which was arranged in the line, but with no linear interaction between these particles. And they found this strange phenomenon, because we know that if you include non-linear interaction into the system, then energy with the time should be distributed through the all modes in equipartitional manner. But it was not so. In this system, they found such strange phenomena. Then, due to the microscope, who was deeply interested in this phenomenon, finally, they found some explanation for this phenomenon, and they, by numerical calculation, showed that the continuous limit of the chain of Fermi pasta Uno is equivalent to Korteweg-de Vries, and in the Korteweg-de Vries equations there is this solitonic waves, and these solitonic waves which interact, which is with each other in some special way, is responsible for this Fermi pasta Uno result. Then this was the explanation of this phenomenon. Then the next, the big discovery was, of course, again due to the main microscope. They found how you can solve exactly the Korteweg-de Vries equation for the solitonic waves. The technique was not simple. It is difficult to explain in some simple with some simple terms, but they showed how you can use the so-called inverse scattering theory of the Schrödinger equations in order to construct the solution of the Korteweg-de Vries equations. This was a quantum theory which you can apply to find some solution for the classical macroscopic equations. This was very interesting, and it was very important for the development of this for the further development of this theory. Then, after this basic breakthrough of the macroscope and all, the next one was due to the Peter Lux. He found the mathematical reasons of the possibility to integrate exactly the Korteweg-de Vries equations and also some another classes of the equations. And he found the instrument, mathematical instrument, how to which you can use to find exact solutions of the so-called integrable differential equations. And after this, it was people recognized that the integrability of the Korteweg-de Vries equations is not a unique, isolated phenomenon, because this phenomenon is much more general, and in many other fields of physics can be found the also differential equations and system of differential equations for which you can apply the same theory which was based, which was discovered by Kruskal and Peter Lux. This is just was the beginning of this development. Then mainly these two persons, Zakharov and Shabat, this is Russian theoretical physicist, developed the contemporary form of this method, and they found how you can calculate in a very straightforward and easy way the exact solidonic solutions of in the integrable systems. And this technique is working up to now. And when you are
in how many dimensions?
Dimension 2, only 2. Because there is just a few examples about the 3 dimensions, but mainly this integrability is working in the 2 dimensions, one time and one space line, or 2 space line. 2 space-like dimensions means stationary fields, and one time and one space-like is solidonic waves. Then these 2 persons created the contemporary form of the method. Then after they create this contemporary form of the inverse scattering method, there was a very wide and very vast development of the theory, which penetrated in many branches of physics, including the biology, maybe botany. The one part of this development also penetrated to the general relativity, and we found with Zakharov the integrable class of the gravitational equation, Einstein gravitational equations, in general relativity. This class of the integrable general integrable gravitational equations was in empty space, just a gravitational field without sources. The first example of the equations with matter, when the right-hand side of the Einstein equations is not 0, was I made this for the stiff matter equation of state, which is equivalent to massless scalar field. And this was interesting because it shows what is written here. If in the beginning of the universe, I applied this for the Friedman universe, and if in the beginning of the universe you have somewhere some local inhomogeneities, then distribution of this inhomogeneity should be local. And during the expansion of the universe, the inhomogeneity disappeared with time. However, this homogeneity leaves some trace behind. And this trace means the gravitational waves of the cosmological origin, which is still exists some time in the universe. Then this was first example when we applied this technique for the non-empty space, when you have sources. The second
scalar field.
Eh?
Only in the case of scalar field.
Oh,
Only.
stiff matter, only scalar field. Yes. Because scalar fields without mass is equivalent from the hydrodynamical point of view to the matter with a stiff matter equation of state. Energy density is equal to pressure. For this case. Of course, this is model. This is not color.
Just P equal O.
P equal O. Because if scalar field has no mass, there is just mathematical duality between these things. The next interesting and important case, when the right-hand side is
P equal over 3 doesn't work.
P
equal O over 3 does not work.
No, don't work. The next was the work of Alexeyev. This is also a Russian mathematician, and he found a way how to generalize this development for the electromagnetic field. And also the charged black holes, Reister, Nordstrom, and Kerr-Newman, was also found to be the gravitational solidus. Then it is interesting that black holes is a solidus. If you will see on the sky, on the galaxy, moving black hole, this will be the same phenomenon like Scott Russell saw in the water channel in Edinburgh.
But in your subatomic solution, you said before, you can have a decay of the solution, and the decay and the source, subatomic, are part of the same phenomenon. Would you have something similar in the case of a black hole?
What you mean under decay? I don't understand.
If you take one of the previous pictures,
Yes.
you said that there was subatomic, then decay, and that the decay part and the solid part.
Yes. Yes, and what is the question?
Could you have this happening for the black hole?
No. This is another thing. Because black holes, which can be extracted from this technique, is stationary solutions. You cannot see any time development. Because again, you cannot...
It's a two-dimension
Two dimension, two space-like dimensions. You cannot see for example, the collision of two black holes, decaying and so on. This is out of the method. This can be, of course, in physics, but it is out of our ability, mathematical ability to find it.
It will be three-dimensional.
Yes, this needs another dimension, time. Then also now we came to the what we are doing now, supergravity. The next model, which was with not empty space, was found by German Nikolai in 1987. And this model is, of course, very interesting and important. However, there is some shortcomings in this construction. The Nikolai constructed integrable supergravity in two-dimensional space-time. You have two-dimensional space-time and a lot of scalar fields and the superparticles in the sense of Euclid's symmetry of these scalar fields. These superparticles are some fermions. And he constructed also the Lux representation, Lux pair for, first of all, he found the physical equations, not from the inner scattering method, just from another sources. And the question how to solve this equation, of course, for this question, he proposed the Lux representation for these equations. This equation should be extracted from the Lux representation. If this Lux pair will be found, then you can have a method, instrument, how to solve this equation. However, this Lux pair, which had been constructed by Nikolai, does not contain the fermionic equation, equations of motion for fermions. It contains only equation of motion for the scalars. And this Lux pair does not cover all the system. Then it is only in this sense it's partly integral models. Then also the mathematical construction of the Lux pair, which was constructed by Nikolai, has some difference with respect to what is we know in the general relativity. And if you have the Lux pair, this is just a typical two equations. It is the pair of equations for the one function psi, and this u and p is a matrix which depends on the spectral parameter, and everything depends on the analytical structure of these matrices u and v in the complex in the complex plane of the spectral parameter. In pure gravity, these matrices u and v are meromorphic and has only the isolated poles with respect to spectral parameter of the first order. And for this system, we developed all the machinery how to solve all this problems.
It's a matrix, not a matrix. It's a matrix.
It is a matrix, of course. Yes, everything here is matrix. And this is complicated enough.
The previous case, in which you had just an equation, a single equation with x and t. Now you have a matrix.
Matrix, yes.
It's not trivial.
Yes. Everything is non-trivial. This is why it is difficult to show all this.
When this matrix concept was introduced, the Lux or what? The matrix, when it was first introduced.
Who introduced this?
Nikolai or
no? This matrix form was introduced by Lux.
yes.
Peter Lux. He was, because Korteweg-de-Vries equation is just one function.
Exactly.
One function, like, yes, and the first, the generalization to the multi-component field was done by Lutz. And from the Lutz, it is continuous up to now.
But your solution with Sakharov and Topov has nothing to do with the matrix. It's your solution with Sakharov, it never used matrix.
It is also used matrix. I will tell you this later. But this matrix is just 2 by 2. It is simple. In the supergravity, this matrix is very big size. Then you see that there was these three shortcomings in the Nicolai construction. Then the question arose whether this model will be covered by our approach. Our work with Nicolai was started in the 1915 and was dedicated just to these questions. How to insert the Nicolai model into our approach and to develop the concrete procedure how to extract from this model the solidonic supergravitational solids. Then you see these equations. In the usual gravity, this GIK has just two values, 1 and 2. And this is a general, usual 4-dimensional gravity. You have two coordinates, t, time, and x, and just a 2 by 2 matrix G. In this sense, what we did with the car is also for this matrix G, but simple enough, 2 by 2. Then to cover now the supergravity model, which was constructed by Nicolai, first of all, we should go to the multidimensional aspect of this our construction. This is easy. And it was done in 79. But in 79, I never published this, but we mentioned about this multidimensional development in our books with Vladimir in 2001. These books about the gravitational solitons was published in 2001. But the first published example of the multidimensional generalization of our method was in our work with you in 1980. Belinski of physics. You remember? You don't remember. There was a paper, Belinski of physics. Yes. And this paper was the first time in history we applied the Belinski-Zakharov approach to the multidimensional space, but only for 5 dimensions. Yes. Then, but this is not a problem to generalize this for any number of dimensions. Then, this was the first step. This was the first step to develop this our method for the multidimensional space. And second was the problem how to insert these fermions. the fermions, if you wish to insert the fermions, you should do the following. You should take the usual, this two-dimensional space and add to this two-dimensional usual bosonic coordinates some set of the Grassmann anti-commutative variables.
For the fermions.
And
For the fermions.
for the fermions, because the fermions will be the fields in this generalized Grassmann space, and of course this you should find a way how to do this. Then this was the second step, how to construct the generalization of our DZ approach to the case where should contain the fermions. Then, if you will do this, then you will see that automatically will disappear this undesirable property of the Nicolai construction, which is due to the existence of the second order poles in the ICM, in the inverse scattering is this first of all. And plus to this, also the condition of the integrability of this generalized Lux representation will also cover the Dirac-like equation for fermions. This was the point which was missing in the Nicolai construction. How to cover the fermionic equations automatically from the integrability condition of the Lux pair.
And did you publish this?
Yes.
Where?
One paper in Physical Review B last year, and this year one paper I published about just the continuation of this.
Electromagnetic field present. Fermionic charge field present.
What means present?
Fermionic charge, electromagnetic charge field present.
No, because for this, this is maybe also possible, but this I don't know, it is not so easy. Maybe you can also construct this for the fermions which has charge. In my construction, which I made yet, there is no charge. It's neutral fermions. And without mass. Neutrinos. Neutrinos. All neutrinos. Because now we know that neutrinos has mass. And maybe 20 years ago there was no mass in neutrinos.
But maybe this will be generalization once you introduce the charge. Well,
Then, if you will do all this, then you will find the fermions, your fermions. You will find in this extension of our matrix G, and this extension is you see that you have in this extension. It of course depends on the number of the anti-commuting coordinates in general, you can do any number of these coordinates. Then from this you can extract the integrability conditions. And there is a huge array of the fermionic and bosonic fields which is in interactions. I calculated only the case with two additional Grassmann coordinates and three. Then three is very difficult, and it is not clear to which physical fields it will be corresponding. This is open question, three and more. But if you have the simplest case, when you have only two Grassmann variables, then in this construction, namely in this construction, is located the Nicolai supergravity model. Of course, this is complicated enough mathematics. Because I forgot to tell about supersymmetry. If you have just an extension of our old technique to the graded algebra for any number of the anti-commuting variables, this in general will have no supersymmetry. If you wish to have supersymmetry, you have to insert into this model some additional symmetry. And if this field G, U, H will take values in the this non-compact group E8, then namely this case will exactly correspond to the Nicolai construction, which will have supersymmetry. Then and what is now? If you have this extended and generalized Flux representation, then you can extract the exact supersolitonic solutions. And the extraction of these solutions is going in accordance with, in principle, in the same way like in the pure gravity. But the only difference is that you should be careful with open differential and algebraic operation. Because you have the graded algebra with anti-commuting variables, then it is you should work taking into account all these super mathematical rules, which is well known. This is not a problem. And there is possibility to construct some exact example of supersolitonic solutions. And this is our activity during the last 2 years.
Now I have only a wish and a hope that the record of this fantastic lecture has been working correctly. It was not presented in the report, but if the record is good, Gabriele of the lecture. We will add the diskette of this fantastic lecture in the ICRANet activities. I think is enormously important. It's not clear the path will be followed well, but the path is sound. I would like to give this message. The path is sound. In other words, we are in a big moment of change in physics, in everything, but especially in physics. There are fields which are definitely healthy, and they have no problems. The physics, the microphysics, solid state field. They are enormously successful. They are promoting the technological development day after day. And they don't worry about fundamental physics, but some application of fundamental physics are certainly there. Then there is another field which is enormously fortunate, which is the field of relativistic astrophysics. Enormously fortunate. Because it's the only case in which a classical fields exist and also a quantum relativistic field exists to describe astrophysics. This is enormously important. We are explaining in ICRANet how to use properly general relativity, black hole physics, and electrodynamics in curved space to do relativistic astrophysics. This is by far another field which is extremely successful. And we are playing a major role. And maybe the major role, without modesty. But then there is another field which started in a grandiose way different, but at least with two giants, Heisenberg on one side, and on the other side, I think, a person fantastic, which was Dirac. That grandiose field developed, but it's in crisis. The theory of that field is missing, the deep theory. Now I dream, after listening this masterful presentation by Valoria, that there has been a new start. I met some of the new start. This new start happened in a fantastic trip of Khrushchev in Soviet Union, where he crossed the border without passport. and had a lot of accidents. But apparently that was the occasion of that fundamental work of Kruskal. By the way, I have in my notebook Kruskal coming back from the Soviet Union, finding a clips in the New York Times, said, Remo, look what the New York Times tells. I have it here. Kruskal. My picture with the black hole idea, presentation. This was one field, but Kruskal was really the key person. And you made a masterful follow of the development of this idea, but the new idea was from Kruskal. Kruskal, of course, I don't know how many of you know, was the man of the Kruskal diagram of the black hole, in and out of the horizon and so forth. But he was a genius and a gentleman. A genius and a gentleman, which not always these two characteristics were present in Princeton. But was definitely a genius and a gentleman and a good friend. And therefore I cannot add anything about this, that there is a new way, hard, very hard. But if we want to understand if a phenomenon with mass and charge comes out, the seed was planted by Dirac. The seed was planted by Carl Newman. The seed was planted by Kruskal. It's the same family. And from this family, all these solitons are coming out, and we are very, very honored to have with us Pescara, one of the major interpreters of this, which is Vladimir.
Martin Kruskal was a really ingenious person, and he deserved at least 2 Nobel Prizes. First of all, the Kruskal diagrams, because due to the Martin Kruskal, now we saw that we know that all points of horizons is just a regular, normal points of the space-time, nothing physically interesting and physically outstanding is on these points. And a lot of people don't understand this up to now. And many wrong papers is appearance now. Because the people don't understand these things. That the horizon has nothing, not physical importance. Second, of course, Kruskal was developed this inverse scattering method and integrated system. It is influence to the theoretical physics of both this achievement of the Kruskal was enormous. This is really 2 Nobel Prizes.
But I think the path you are following with Nikolai, to me, seems the correct one. And everybody, but I will give you the cassette of this and listen.